This first revision model is going to cover the fundamental topics of linear algebra that are useful for the context of reliability theory. So as you're going to see throughout the progression of the class, linear algebra is really going to be the foundation of everything we're going to be with structural or system reliability. All the equations we're going to use are going to be building upon these building blocks. So what we're going to see in this revision module, first, what is going to be the notation we're going to use throughout the class, what are the fundamental operation we need, and finally, how can we operate and do transformation in linear system using linear algebra. So that puts us at that first module 0 revision for linear algebra. So first, notation, scalars, vector matrices. So if we start with scalars, so scalar is going to be just one unique numbers. So I can say that x belongs to, say here, the real space. So from minus infinity to plus infinity. It could belong to the positive real space from 0 to infinity. This is equivalent. So it's z, integer numbers, from minus infinity to infinity, but just integers. It could belong to the interval 0, 1, including both 0 and 1, or 0 excluding 1, okay? So this is for scalars. Now, if we look at vectors, vector is going to be kind of a 1D table containing numbers or scalars. So in this case, it's going to be an n-dimensional vector. So if ever I want to represent a vector, it's going to be a lowercase x bold, okay? It's not only going to be x, but a variable name bold. Whenever I would write something on the board, it's hard to make a clear bold case, so I would underline it. And we can say that if, for example, each element of my vector x, so the subscript after my brackets represent I want to access the ith element of my x vector, belongs to R for all I in 1 up to n, we can see that x is defined in an n-dimensional real space. Okay, so these are two ways of defining it, either the multivariate way or element by element. Now, if we switch in a 2D space for matrices, we can see this as a 2D table that this time, again, is going to contain either numbers or a scalar. So now we're going to represent the matrices compared to a vector by the uppercase x bold, okay, or uppercase variable name bold. If I would be to write this on the board, it would be capital X underscore, okay, to distinguish it for the bold case. Now, the first indices here represent the row index, and the second, the column index. So the mth line, the nth column. So we can say again, analogously to what we did for vectors, the ith and jth indexes of x belongs to a real space, or equivalently, for all I from I to m, the column indexes, the rows indexes, or for j from 1 to n, we can say that x belong to a m by n space, so m line and column that are all in the real domain. For matrices, we can have a square matrix. Okay, if we say that x is a square matrix, we're going to have as many rows as we have columns. And we can say again for this that x is going to belong to a r n by n. It doesn't have to be r, but in this case, it's just an example. But the important case is that we have as many rows as we have column in a square matrix. We can have a diagonal matrix. So again, a square matrix, but which has a particularity that we have only non-zero term on the main diagonal. So it's a square matrix and only that main diagonal as non-zero term. So we can see in terms of notation, if x is a vector, diag of x is going to make such a square matrix. We have special square matrix or special diagonal matrix, which is the identity matrix we're going to denote by I. So this is a diagonal matrix, but which the main diagonal terms are only 1, everywhere else is 0. And it has special property. For instance, if we do I, my identity matrix, times x, a vector, that doesn't change the result of my vector. I times x, a matrix, it remains my same matrix. So identity matrix, when you multiply it, it's like multiplied by 1. Okay. So if we look in Python, how can we do these basic operation? If we look if we use the package numpy and scipy, we can define matrix A using numpy 1 and 3 rows, 2 column. Okay, it's going to be a 3 by 2 matrix filled with ones. We can do I5. That's going to be a diagonal matrix with 5 by 5, not a diagonal, identity matrix with 5 by 5 in dimension. So now if we want to manually build a matrix, we can say np array. So the first line is going to be 1, 2, 3. The second line is going to be 4, 5, 6. Then if I want to access some element of C, so say I want to have 1 and 2. So Python is 0 index. So what it means, I want to access the second line, the third column. So second line, third column, that's going to give me 6. Then if I want to access not only one specific element, but a whole line or a whole column, I can do so by saying 0 and double dot to say everything. So this is going to be the first line, 1, 2, 3, all the columns. So the result is going to be 1, 2, 3. And finally, if I want to take the element of E, which is 1, 2, 3, and build a diagonal matrix from it, I can do diag of my vector is going to build a 3 by 3 diagonal matrix. Now for the operation involved in linear algebra, we're going to look at transposition, multiplication, and inversion. So if we have a matrix, in this case, a 2 by 3, and I transpose it, what I'm going to do is that I'm going to permute what was initially a row becomes a column. Second row, second column. Okay, this is what transposition does. So basically, if I have a vector x here, if I permute the indexes I and j, it's like x transpose ij. Okay, this is equivalent. Then we have multiplication. Imagine we have two matrices A and B. We multiply them together, doing a matrix product. We're going to obtain a matrix C. And equivalently, whether we put an X or we put nothing, we imply matrix multiplication. And matrix multiplication has special property. How it works is that we're going to say, to obtain the ith and jth terms of C, I'm going to take the ith row from A, and I'm going to take the jth column from B, and I'm going to sum the element-wise product of all the kth term for both. So this required that the matrices we want to multiply have compatible dimensions. So for instance, if A is m by k, so the second index representing the number of column must match the number of rows of the matrix I'm multiplying with. And then we have B that has n column. And the resulting matrix C is going to be m by n, the starting indices and the finishing indices. If we look at this visually, I want to multiply A, which is a 4 by 2, with B, which is a 2 by 3. So the resulting is going to be a 4 by 3. Okay, so for instance, for the term 1, 2, I'm going to have A11 times B12 plus A12 times B22. Okay, same thing for my other term, 4, 3. There are some specific rules we can use with linear algebra for the multiplication of matrices. The first one is distributivity. So what it means, if I have parentheses like this, A times B plus C, I can distribute my A inside my parentheses. Then I can use associativity. So if I have parentheses like this over multiplication, I can move around the priority of my operation without changing the result. If I have A times B, in most cases, it's not equal to B times A, okay? It's not commutative. I can have a vectorial product. So typically when you see that little dot, it means that you're going to do an element-wise product of your vector, the elements of your vectors, and then you're going to sum them over. This is equivalent to do X transpose times Y. So this is for the property. Now we're going to look into what we're really going to build upon for reliability theory, which are linear system. So here you can see a little line, a linear system, a very simple one, where you build a relation between an output y and an input x. So in this case, y would be equal to 3x plus 1. Okay? If we want to represent this in a kind of generic term, we can say this is y equal ax plus b, where a would be 3, b would be 1. Then we can extend this to a 2D system. So there's still one output y, but there's two input, x1 and x2. So y equal x1 plus 2x2 plus 3. So we can represent this in a vector format at A transpose X plus B, where A is not a vector of coefficient 1 times x1 and 2 times x2, so 1, 2, where B is going to be my tree, and my X is going to be a concatenation of my two-dimension x1 and x2. And the powerful thing about this representation is that we can generalize it to an arbitrary large number of dimensions. And it's very efficient to compute, it's very efficient to represent. Last operation we want to see is inversion, when we want to solve linear system. So if we take the inverse of a matrix multiplied with itself, it's going to give us the identity matrix. And we can use this to solve linear system. But to be invertible, a matrix must be first square and must not have linearly dependent rows or columns. So if we want now to use this to solve a system of linear equations, say ax equals b, what we're going to do is that we're going to multiply each side by the inverse of my matrix A. We saw earlier that A inverse times A is going to give me identity matrix. And we saw earlier as well that identity matrix times a vector doesn't change it. So I'm going to have X, that's going to be what I'm looking for, is going to be equal to A inverse times B. As I said, we have solved now for linear system for X. So basic Python operations for these operations from the NumPy module. So 1 3 by 2. So again, a matrix of ones, 3 rows, 2 columns. Now I can build a manually defined matrix. First row 1 2 3, second 4 5 6. I can access some term of that matrix. So I'm going to take the first two the first two rows of B, the first two column of B. Okay, again, 0 index Python. So it's going to be a 2 by 2 matrix. Then I want to take that matrix C and I want to invert it. Okay, so NP, NumPy, linear algebra, inverse. So I'm going to invert my matrix C, and then I can multiply A, what I defined earlier, times B. Okay, notice that the dimension match. The second dimension is 2. The dimension of D is 2 by 2. We can multiply them. So at is the matrix multiplication symbol in Python. Then if I do A star B, so this is not a regular product. This is an element-wise product. I'm going to multiply all terms in a vector matrix term by term. So the change of the final result is not going to be changed. And here B, I can transpose it. So G, what I want to do, I want to solve a linear system. So I'm going to do the inverse of my matrix F. I'm going to multiply it by B. Okay. This is what the typical operation you would use in linear algebra. So last thing we're going to look at is how can we see linear system as transformation of our space. So let's look at what I have plotted here for a space x1 and x2. So I've plotted this circle. How do you plot a circle? Okay, and typically you're going to choose some value x, in this case x1, over which you want to plot from -1 to 1. And you're going to compute the equation of a circle. And a circle is the square root of 1 minus x1 squared, where we have two values for the square root, the positive and the negative. So I'm going to plot the values for the square root of the positive. I'm going to plot the value for the square root of the negative. Okay, now I'm going to just make a line that link all those points. This is how I would draw a circle. And now I want to operate on each point I draw here, which are two coordinates, basically x1 and the corresponding x2 given by my formula of the circle. So if I define the space over which I plot x1 and x2 in a matrix where we have all the components of x1 and x2, and then I want to see what if I have matrix A and I deform the space on which I plot, okay, by doing A x transpose. I'm going to get a new vector or a new matrix x prime. So if the matrix A I multiply with is an identity matrix, I don't change my scale at all. But if I change my value and now my matrix A is as a 2 on the 2, 2 component, then we see that I'm going to modify my second dimension x2. I'm going to scale it vertically by a factor 2. And what we're going to see here is that if we look at the determinant of my matrix A, we have 2. Why? Because the determinant measure by how much my matrix A scale my space. Here I scale my space by a factor 2. So by effect, I scale the area of my circle by a factor 2. If instead of having a 2 there, I would have 1.5 and the 1, 1 component, I'm going to affect only my x1 dimension. I'm going to stretch it by a factor 0.5. If I have terms off diagonal, I'm going to affect both dimensions simultaneously. I'm going to kind of skew my space. Now I'm going to shrink a little bit. My determinant is going to be 0.75. If I push that to the extreme, I put 0.9. I'm going to really, you see the original grid in the background? You see the deformed grid in blue with a circle that is all squashed on itself. And if I go with some even more extreme value, say point, I don't have even more extreme value, but the more you're going to make, it's going to almost look like a line. So that concludes the first revision module where we wanted to see the key concept for linear algebra.